Imagine vanishing into the thin air, not in the mystical sense, but literally disappearing due to a sudden absence of space itself. Or consider a world where time reverses its flow, enabling you to witness the beginning of the cosmos just as easily as its end. Although these scenarios sound like they belong in science fiction, they serve to underscore the profound and often bewildering nature of two fundamental constructs that dictate everything from the decay of stars to the beating of our hearts: space and time. These concepts are not merely backdrops on which the universe plays out. They are dynamic, interwoven fabrics that define the cosmos. In this essay, we will embark on a journey through the labyrinthine concepts of space and time. What are space and time? At their most basic, space can be thought of as the vast container that holds all matter and energy in the universe, while time is what we use to describe events, sequence, and duration. They are the stage and the timer that orchestrate the cosmic dance of celestial bodies, as well as the smallest particles in the quantum realm. Despite their apparent simplicity, space and time are anything but. These concepts have perplexed scientists, philosophers, and thinkers for centuries. As we delve deeper into their nature, we uncover layers of complexity that challenge our most fundamental perceptions of reality. In this essay, we aim to simplify these complex ideas through clear explanations and real-world analogies, making them accessible to those curious minds eager to understand the underpinnings of the universe. Historically, the concepts of space and time were viewed as absolute and independent entities. Ancient civilizations, like the Greeks and Indians, had their interpretations, often tying them to their understanding of the cosmos and divine elements. However, it was Isaac Newton who crystallized the idea of an absolute space and time in his Principia Mathematica. Newton posited that space was a vast emptiness, extending infinitely in all directions, within which the objects of the universe are located. Time, on the other hand, was seen as a separate, relentless flow that occurs at a constant rate throughout the universe, unaffected by the events within it. This Newtonian framework dominated scientific thought for centuries, until the advent of Einstein's theories in the early 20th century. These theories would challenge the very foundation of Newton's understanding and transform our conception of space and time forever. Albert Einstein, in the early 20th century, proposed two groundbreaking theories: the special theory of relativity in 1905 and the general theory of relativity in 1915. These theories revolutionized our understanding of space and time, highlighting that they are not static, absolute entities as Newton had suggested, but dynamic quantities that interact with matter and energy. Special relativity introduced the idea that the speed of light in a vacuum is constant and that nothing can travel faster than light. It showed that time can dilate, slow down, and lengths can contract depending on the speed at which an object is moving relative to an observer. This was a radical departure from Newtonian mechanics, implying that observations of time and space are relative to the state of motion of the observer. General relativity went further, describing gravity not as a force acting in space and time, but as a curvature of space-time itself, caused by mass and energy. This suggested that massive objects like stars and planets could warp the fabric of space-time, affecting the motion of other objects and the flow of time near them. These concepts are not merely theoretical, they have practical implications, influencing everything from the orbit of planets to the functioning of our GPS systems. The notion of the space-time continuum combines space and time into a single four-dimensional construct. This idea, central to general relativity, posits that the three dimensions of space and the one dimension of time are intertwined, forming a fabric-like continuum. Space and time in this model are not separate entities, but are connected dimensions that respond to the presence of mass and energy. This interweaving means that any event that occurs in the universe involves both space and time dimensions. The classic analogy is that of a trampoline. When a heavy object is placed on a trampoline, it causes the fabric to deform. Similarly, in the universe, planets and stars curve the space-time around them, and the deformation affects how other objects move and how time passes in that region. Einstein's theories, despite their abstract nature, have concrete applications that affect our daily lives. One of the most well-known applications is in the technology of global positioning systems, or GPS. GPS satellites orbiting the Earth must account for the effects of both special and general relativity. Special relativity predicts that because the satellites are moving at high speeds relative to an observer on Earth, their clocks will seem to tick slower. General relativity, on the other hand, suggests that because these satellites are further from the massive Earth, their clocks will tick faster due to weaker gravitational effects. The net result is that, without corrections based on both of these theories, GPS technologies would fail to function at their current level of accuracy. Another everyday effect of relativity is seen in the phenomenon of time dilation observed in astronauts. Those who spend time in space age slightly slower compared to those on Earth, due to the high speeds at which they travel. Quantum mechanics, a pillar of modern physics, deals with the behavior of particles at the smallest scales. It introduces a realm where the deterministic laws of classical physics give way to probabilities and uncertainties. When quantum mechanics is considered in the context of space and time, the waters become even murkier. In the quantum world, particles can exist in multiple states simultaneously, and their properties are not definite until they are observed. This introduces a level of uncertainty to the very fabric of space and time, suggesting that on the smallest scales, space and time may not be smooth and continuous, but instead grainy or discrete. Furthermore, quantum mechanics posits phenomena such as entanglement, where particles can become linked, and the state of one, no matter how far apart, can instantaneously affect the state of another. This challenges our traditional concepts of causality and the flow of time, leading to new and exotic theories, including the possibility of a quantum theory of gravity that attempts to reconcile the quantum world with the theory of relativity. The theories of relativity and quantum mechanics, while challenging to grasp, are not without empirical support. Numerous experiments have validated the predictions made by these theories, cementing their place in the scientific canon. One of the most famous tests of general relativity was the observation of the bending of light by gravity during the solar eclipse of 1919, led by Sir Arthur Eddington. This expedition aimed to measure the deflection of starlight passing near the Sun, a phenomenon predicted by Einstein. The results matched Einstein's predictions and were hailed as a major confirmation of general relativity. In the realm of quantum mechanics, the double-slit experiment famously demonstrated the wave-particle duality of light and electrons, showing that particles can exhibit characteristics of both particles and waves, depending on the experimental setup. This experiment has profound implications for the nature of reality and our understanding of space and time at quantum scales. The exploration of space and time raises as many philosophical questions as it does scientific ones. These questions delve into the very nature of reality, existence, and our place within the universe. For instance, if time can dilate and contract, what does that say about our perception of time as a constant flow? Does the possibility of time travel, suggested by certain solutions to Einstein's equations, imply that the future is predetermined or that the past can be altered? What does the entanglement of particles mean for our ideas about causality and connection? These questions are not just academic, they affect how we conceive of free will, ethics, and the nature of human consciousness. As our understanding of space and time deepens, so too does our understanding of ourselves. The study of space and time is far from complete. Emerging theories and technologies continue to challenge our understanding and open new fields of inquiry. For example, the theory of loop quantum gravity suggests that space-time itself might be made up of tiny loops, a quantum property that could reconcile the gravity of general relativity with the quantum mechanics world. Additionally, the ongoing search for dark matter and dark energy, substances that together comprise most of the universe's mass energy content but remain mysterious, could dramatically alter our understanding of the cosmos and the fabric of space-time. Technological advancements, such as new types of telescopes and particle accelerators, promise to provide further insights into the nature of space and time. These tools may one day unlock secrets that today we can hardly imagine, possibly revealing more about the early moments of the universe or uncovering new fundamental forces. Space and time, as we've explored, are far more than mere stages on which the universe unfolds. They are dynamic, interrelated aspects of a complex fabric that dictates the behavior of everything in the cosmos. From the orbits of planets to the workings of our GPS devices, from the potential for time travel to the philosophical implications of quantum mechanics, understanding space and time is central to understanding the nature of reality. This essay has journeyed through ancient conceptions to modern scientific theories, each layer adding depth to our understanding of these fundamental concepts. As we continue to explore and question, the mysteries of space and time remain at the forefront of our quest for knowledge, reminding us that at the heart of all scientific endeavor is the drive to unravel the universe's most profound secrets. The essay provided explores the intricate and interconnected nature of space and time, presenting a comprehensive overview accessible to those without a physics background. It delves into historical perspectives, theoretical advancements, and the philosophical implications of our understanding of these fundamental entities, inviting readers to contemplate the profound influence they have on our perception of the universe.